to share my screen. Okay. So, right. So a few questions have been pouring in. So yes. So if parents, if you were here, thank you very much for attending. The next part is just physics. Of course, by all means, this is webinars can be attended by anyone. Yes, and just looking at some of your questions. Oh, okay, chat, of course. Okay. So, will there be solutions? No, unfortunately, we don't give solutions. How much time is typically needed to work on weekly assignments? So, yes, Professor Lvovsky said 10-15 hours for each. So that's in 4 weeks. That's about that's about 5 to 7 hours per week. Okay, realistically, I'd say a minimum of 4 hours. Realistic on average, our students tend to work about 7 hours a week. Okay. Right. Where does your curriculum previously shown play a part in the COMPOS for year 11s? The current year 11s do the year 10 program, and next year you do year 12. But if you're in year 10, this year you do the year 10 program, and next year you do the 11 program, and then year 12 and year 13. Okay. So we weren't initially planning to accept year 11s, but then we felt that we don't want you to miss out. And so we started accepting year 11s, but we only have the year 10 program. As of now, the year 11 program is not designed yet. So this will be designed for next year. So this is why year 10 and year 11s are together this year. If you complete COMPOS 1 year, do you automatically get admitted into the next year? Yes, there's an answer to that. You need to have done at least half. Yes, so aim for a minimum of 50%. Although we won't kick you out if you submit 45% consistently, as long as you're consistent. If you as long as we feel that you're putting in effort, that's pretty much the idea. When will our first tutor class be? Optimistically, in a week's time. Okay, so hopefully we can start next week. We need to install special software for the class use Zoom, or like what we are doing? Well, it depends on your tutor. Your tutor will tell you what to install. So because different tutors use different platforms. We have Jitsi, we have Zoom, we have Teams. So it depends on your group. Yes, so your small groups decides what they are more comfortable with. Will we know? Okay. Yes, you can always talk to your tutor. Your tutor is the first go-to place. Will we go through the first assignment we already did in tutorials? In your tutorial, you can ask your tutor to go through some of the questions. Yes. How many year 11s were accepted? Quite a few, actually. I think around 80. How do you know what was wrong with the assignment? You ask your tutor. So if you're in year 11, do you work till July or February? So in year 11, you do until February. We don't want you to miss out on your GCSEs. Yes, so we are not that horrible. So in February, you do the first 6 assignments of year 10 in year 11. The first 6 assignments of year 10, then year 10 continues and year 11 stops. and goes to do their GCSEs or equivalent exams if you are not in the if you're not doing GCSE. There will be 10s in the same tutorial group as year 11s. No, there will be different different tutor groups. Will the year 11 program finish later than February? Well, no, it won't finish mid-February. Are there six assignments? 6 per subject. Yes, so 6 physics, 6 maths. Will there be solutions to the problems or feedback? Feedback, yes. Solutions, unfortunately, no. Do I have to take both physics and maths A level to continue to COMPOS next year? No, you don't have to, but like we tend to have in year 12, we tend to have 100% of our students do physics and maths, and 75% of our students do physics, maths, and further maths. So this is the typical distribution of our students. So you don't have to take any of the A levels, but we just think you'll find it tough if you don't do physics, for example, to do COMPOS. If you do COMPOS, you'll pass physics A level with flying colors. I mean, it would be very easy for you. Right, Rachel, if you would be so kind to answer some of the questions in the chat, because so I can actually get a move on with electricity. So the electricity, so it's has been published only today. We were incredibly busy. So if you're not sure where to find the assignment, you go to our website, and on the first page it says download assignment 02 here. Or you can go get involved assignments. Both take you to the same place. Assignments, and then physics 1002. This is for year 10 and 11. You can see that. Right, so we are going to talk about charge, current, voltage, lots of things, of course. Yeah. And the first thing I would like to do is just to introduce you to some concepts. And the first exercise is literally, well, I want you to develop an intuitive approach to electricity, to electrical circuits. And so we have a 12-volt battery, and we have 2 identical resistors. So what do you think the voltages are going to be on each of these resistors? So please answer in the chat, or shout out if you're brave enough. 6 volts. Yeah, 6 volts and 6 volts. Of course, because this is how voltage works. Voltage is energy, right? It's the energy transferred. So the battery gives energy, and this energy is dissipated in the resistors. Okay, so this is explained in the video, in one of the videos that is posted in the assignment. Right. Okay, and this is very intuitive. Now you have a 24-volt battery, and you have 2 resistors, 5 ohm and 10 ohm. What are the voltages now? Ooh, me now? Yeah, very good. Well, actually, no, you got them the wrong way around. 6 and 18, 8 and 6, 8 and 6. Yes, that is correct. This is going to be 8 volts, and this is going to be 6 volts. Oh, sorry, 16 volts. How does that work? Well, it is twice as hard. So the current goes around the circuit. And it's twice as hard to go through this resistor than through this resistor. So you lose more energy is lost in the 10 ohm resistor. More energy is lost in the 10 ohm resistor. You can think of this as 24 joules is given to each coulomb. So each coulomb of charge received 24 joules of energy. And then some of this energy dissipated in the first resistor, and then some of it dissipated in the second resistor. I love this simulation. So FET circuits, I recommend you use it when you're doing electricity problems, especially when you're not sure what's going on. So yeah, so we have a battery, we have a resistor, so the battery is 24, 5, and 10. So this is 24, and this is 5. And the other one is 10. So we take a wire, we connect it. Okay, and you can take a voltmeter, and this is 24 volts. This is 8 volts. And this is, of course, 16 volts. Okay, so it works. So the voltage is split between components proportional to proportional to the resistance. Proportional to resistance. Okay, so we have 24 volts split between 3 resistors, a 7, a 3, and a 2. So give it a go. What are the voltages? Especially V1 is 14. 14, 6, 4. Very good. 14 volts, 6 volts, and 4 volts. Is there anyone here who did not know how to do this before, and now you do know? Type 1 in the chat, please, and type 0 if you're still unsure. Oh, very nice. Very nice, lots of ones. If you 1, it means that you didn't know how to do it, but now you know. Okay. I call this intuitive approach because if you take if you look at these, so this is a book. This is an old book, by the way. It even has the old resistors because we don't draw the resistor like this anymore. We use this symbol for a resistor, of course. But in the States, they still use the zigzag. But this is an old O-level book, so this is from the 80s. It is still very valuable. I found it in the school I worked at. I found it in the drawer, and somebody said, "Oh, we need to throw these books out." I said, "No, this is the best book ever." Okay, so this, of course, we have 2 resistors, so we don't know the voltage here, but we know that this is 9 volts, and this is an 18. So this is 3 times less. So this must be 3 volts. So this is 9 volts. This must be 3 because it's 3 times less than that. So this must be 12 volts, of course. And all right, now, let's see if anyone can do 5 and 6. So these are tough. Can anyone do 5? I'd say they are questions with a star. For the year 11, they run until February. They don't resume after the GCSE. After the GCSE, you can join year 12, right? 4. Sai Ritwik, you said 4. You are correct. Can you explain why? And Otto, you're correct. Can you explain why? The 6 ohm resistors are in parallel. In total, it is 3. Yes, well done. You can see that this is a 6 and another 6, but they are in parallel. In resistors in parallel, the total resistance decreases. So we can remove this resistor and replace it with a 3 ohm resistor. And this is a 3 and this is a 2. So it's the proportion. This is 4 volts and this is 6 volts. So the answer is 4 volts. We have a Christmas break. We have a Christmas break. Why the resistance decreases? Well, a resistor is like a narrow door, a narrow passage. So imagine you are walking and there's a narrow passage. It's hard to get through. So imagine a crowd of people, like imagine 1,000-year sevens trying to go to the trying to have lunch in the canteen, and they're all trying to run through one door. So 1,000 people running through one door, and now we have 1,000 people running through 2 doors. Well, it's 2 times easier. 2 times easier to pass 1,000 people through 2 doors there rather than through 1 door. That means if you have this is a 6 ohm resistor, the total resistance is 6 ohms. But if this is a 6 ohm resistor and this is a 6 ohm resistor, the total resistance is 3 ohms. Another pathway will make resistance less, exactly. So you can replace 2 parallel resistors with one with a lower resistance, and you can replace 2 series resistors with one if they with a higher resistance. Basically, we're continuing to try to grasp a feeling of electricity. Now this one is tougher. I would say this is 2 stars, and somebody is saying 1/R1. Ooh, very, very good. Yes, but if the resistors are identical, then you just divide by 2. Sahana. That's a very good question. But if the resistors are the same, it works out. You just need to divide by 2. I'm going to skip question 6, and let's go to ammeters. Ammeters by proportion. So ammeters work in this interesting way. So if you take an ammeter, this is not the ammeter you're used to. This is called a non-contact ammeter. You can actually use them. You can actually buy them. it looks like this, a non-contact ammeter. It looks like this. So you put the wire through the loop, and it actually measures the current. So where is it? Here it is. So you just hold the wire, and it tells you the current in that wire. Yes, it measures the magnetic field strength. Correct. Oh yes, thank you, Rachel. Thank you very much. And yeah, so a non-contact ammeter. So we can measure it here. So it's 1.6 amps. You measure it here, 1.6 amps through the resistor, 1.6 amps, 1.6 amps. So in a series circuit, well, you know this from year 8 probably, that in a series circuit the current is the same. Okay, so there's nothing troubling about this. So we can easily answer this question. So if this is 3 amps, that means so the current is flowing that way. So this is 3 amps, this is 3 amps, so this is 3 amps, and this is 3 amps. Right? There's nowhere else for current to flow. So with current, it is the same all the way around. Okay, now we have 4 amps of current flowing through here. Well, that means 4 amps. It's still 4 amps, still 4 amps, and still 4 amps. There's nothing you can do about it. There's 4 amps. And now they have 6 ohm and 6 ohm. The current splits, of course. This is going to be 2 amps, and this is going to be 2 amps. And then the current rejoins to make 4 again. Now we can check this, of course. So we can take 2 resistors, a battery, and a wire. Okay. Okay, so, well, this is 10 and 10. You can see this is 1.8. Okay, let's increase that. 4 amps. You can see this is 4 amps, 4 amps, 4 amps. But then the current splits into 2 and 2 amps. 2, 2, 4. And then the current rejoins to make 4 again. So this is how it works. Okay, any questions? Any questions? Okay. So, A1, A2, A3. Who can help me with that? A3 is 3, correct. A3 is 3 amps. 1.5, 1.53. Okay, so different ideas. So people think that A2 is 1 amp and this is 2 amps. Okay, right. I think we need to do an experiment. How about I give you a task and you actually do it. So here's a link. Build a circuit. Here's a link. Make a circuit. So we have 4. What are the resistances? 4, 2, and 6. 4, 2, and 6. Sahana, yes, the current would take the path of least resistance, of course. Right. I'd like you to give it a go. Remember, Professor Lvovsky said that you learn only when you do stuff. So you need to make a circuit. You don't need the ammeters. You just take one ammeter and grab it. Less resistance, so more current. A1, 1 amp. A2, 2 amps. RB, yes, you are correct. So this is incorrect. So who's managed to do it? I'll give you one more minute. So it can look like this. This is 6 ohms. 6 ohm. This is 4 ohm and 2 ohm. 4 ohm and 2 ohm. And the current is 0.73, so we can increase the current, increase the voltage until it is 3 amps. Okay, here we are. So let's have a look. So we this is 3 amps, and this is the 2 ohm resistor, and this is the 4 ohm resistor, and we see that this is 1 amp, in fact, and this is 2 amps. Because there's a higher resistance here, we have less current. And you can see the electrons are actually moving slower through this resistor because it's harder. It's harder to pass through this resistor. It's easier to go through. Current chooses the least resistive path. So it is going to go like this. So therefore, we have 1 amp going here and 2 amps going here. So this is the intuitive approach to electricity. So question 4. Question 4. There's lots of them. So let's start with A1. Anyone? Actually, you know what? I won't. Yeah, it's 2.5. So we have 10 amps here, and 10 amps flows through here. So this is plus, this is minus. Current goes from plus to minus this way. The current splits here and here, here and here, here and here. So effectively, it has 4 different pathways to choose from. And 10 amps, and these 4 paths are equally likely because they're all 5 amps. So this is going to be 2.5 amps. So 2.5 amps and 2.5 amps, and here 2.5 amps. Now 2.5 and 2.5 join together to make 5 amps here. Then 5 and 2.5, they join together to make 7.5 amps. And that's it. That's the question. Okay, so that's that. So we have spoken about voltage and current. So we will need some formulas, of course. Then what do we know about voltage and current? So first of all, we know that the current is equal to the charge over time, charge that flows over time taken. We know that the voltage is the energy transferred divided by charge. Voltage is the energy transferred by per charge. We need power. Power is energy divided by time. And from here, I can express energy. Energy is equal to QV. And from here, I can express time. Time is equal to Q over I. And if I plug that in, energy divided by time. So energy is QV divided by T, which is Q over I. Q cancels, and this simplifies to VI. So power, electrical power, is voltage times current. This is an important formula. We also need to know the resistance. The resistance is defined as voltage divided by current. And from here, I can express voltage. Voltage is equal to IR. I can plug that into here, and I have another formula for power. Power is V, which is IR, times I. So it's I squared R. Yes, here's the link to the page, to the whiteboard. And if I can also express I is equal to V over R, I can stick that into here. P equals V squared over R. So these are three formulas to calculate power. Important formulas, by the way. They are all in GCSE, so there's nothing new. I'm not teaching you anything new at the moment. Right. And okay, so I don't think there's anything else we need for electricity. So let's get to it. So problem 3, in the circuit, find the total resistance of the circuit. Well, that's easy. That's 200 because it's 150. That's 200 ohm. The current flowing through each resistor. Well, we know that the current, so the current is the total voltage divided by the total resistance. Total voltage, and the total voltage is 240 divided by total resistance 200, which makes it what, 1.2 amps? 1.2 amps. And because they are in series, it has to be 1.2 amps each. The voltage across the 50 ohm resistor. Well, the voltage across the 50 ohm resistor, voltage, as we know, voltage is IR. IR, so its voltage is 1.2 multiplied by 50, which is 60 volts. Yeah, so this is 60 volts. And the power dissipated in the 50 ohm resistor. The power dissipated in the 50 ohm resistor. Well, power is VI. So D. Power is IV. So current is 1.2 amps multiplied by V, which is 60, which is 72. Yeah, 72. Yeah, 72 watts. Now, could I have used a different formula? Of course I could. I could have used this formula, I squared R. So I squared is 1.2 squared multiplied by R, which is 50, which also gives you 72 watts. Could I have used the third formula, V squared over R? Of course I could. It's 60 squared divided by R, which is 50. So 60 squared is 3,600. 3,600 divided by 50 is 72 watts. So it doesn't matter which formula you use, they're all valid. The voltage across the 50 ohm resistor. The voltage across the 150 ohm resistor, so E. So in here, what I'm demonstrating is you need fluency, is that the fact that you need fluency when dealing with these formulas. You need to be very confident with them. If you're not, just download a bunch of questions, like just practice. Isaac Physics is a great resource. If you go to Isaac Physics, let me have a look. Isaac Physics, GCSE or equivalent, mastery book, and electricity. So literally all of these. Yeah. So if you don't know where to practice, here you are. There's a bunch of questions: charge and current, charge and voltage, circuit rules, resistance, characteristics, power calculations. So all of these are really valuable if you're not confident with formulas. Okay, E, the voltage across the 150 ohm resistor. Well, that's easy because this is 60, so this has to be 180 volts. It's 3 times more. The power dissipated in the 150 ohm resistor. So power, I'm just going to use any formula. I'm going to use I squared R. So it's going to be I squared, which is 1.2 squared, multiplied by R, which is 150. So that's going to be 216 watts. Gosh, I'm quick at calculating today. Anyways. Right. So this is pretty much it. The next topic is combinations of resistors. So some of you already know how to calculate. So if you have in series, if you have resistors in series, then the total resistance is R1 plus R2. It doesn't have to be limited. It could be R3 plus R4, etc. But we'll stop with 2. And in parallel, the total resistance is 1 over total resistance is 1 over R1 plus 1 over R2. So let's calculate this parallel combination. So R1 is 300 and R2 is this. So question 1, 1 over R1 plus 1 over R total is equal to 1 over R1 plus 1 over R2, which is 1 over 300 plus 1 over 600, which you multiply this by 2. So it's 2 over 600 plus 1 over 600, which gives you 3 over 600. And but this is 1 over RT. This is 1 on 200, which is 1 over RT. So RT is 200 ohms. So this is 200. This is another 200, and this is 53. So the total is 453 ohms because these are in series. Series is easy. Okay. So this is straightforward. But from here, if you only have 2 resistors, so for 2 resistors, there's another formula you can use. For 2 resistors, you can do 1 over RT is equal to 1 over R1 plus 1 over R2. You can multiply this by R2, multiply this by R1, and you get R2 plus R1 divided by R1, R2. And you can flip both sides. You can flip both sides. So from here, you have 1 over RT is R1 plus R2 over R1, R2. If you turn them both around, you get RT is equal to R1, R2 divided by R1 plus R2. And this is a very useful formula when you have 2 resistors, because it's easier than dealing with 1 over R1 and 1 over R2. So let's use this formula here. So it's going to be 300 times 200 divided by 300 plus 200, which is 60,000. No, 60,000 divided by 500. 600 divided by 5, that's 2. That doesn't make any sense. Where did I go wrong? Oh, 300 times, of course. Sorry, messed it up. It's 300 times 600 over 300 plus 600, which gives you 300 times 600 is 180,000 divided by 900. So 900 cancels. So that's 200. Works. Yeah. See, you got the same result using a different formula. Well, it's not a different formula. It's just a rearrangement of the previous one. Nothing extraordinary there. Question 2. It's tougher, but I mean it's the same. So these are just added, so that's easy. So all you need is this combination. You can't use the new formula because this only works for 2. This is 3, so again 1 over 200. So 1 over RT, the total. 1 over 200 plus 1 over 500 plus 1 over 1,000, because this is a kilo ohm, so there's 1,000 ohms. So 1 over RT is equal to, so we'll multiply this by 5, multiply this by 2. So 5 plus 2 plus 1 over 1,000. So RT is 1,000 divided by 8 ohms, which is 125 ohms. So this is 125 ohms. So this parallel combination can be replaced with 125. So 450 plus 250 plus this. So that's what, 700 plus 1,000, 1,125 ohms. This is the total resistance. So you have some similar problems to that in the assignment. And then here, what you do is 16 plus 12. So that's 16 plus 12 is 28. 28 and 14. So this is 28. So this is 28. And then 28 and 14 in parallel. It's going to be less than 14. And just, yeah, just carry on. Nothing extraordinary here. Right. The next one is a scary one. But this is an example of a question where you cannot use you cannot represent it as a combination, because if you look at the previous one, so you can combine these two, so that's going to be 55, and then these two are in parallel. These two are in parallel, so you replace them with 1. So basically, what do you do here? You have 1.5, 1.5, then you have 18 and 43. 43 and 11 is 55. And then 1 and 2 is going to be 0.67. That's going to be 2/3. 0.67. These two. And then 18 and 55, you combine them, you get something else. Yes, you get 1.5 plus this, and you just add them, right? So this is easy. This one is impossible to do this way. It doesn't work. Here you have to use Kirchhoff's laws. Kirchhoff's laws, and the first Kirchhoff's law is that the current Kirchhoff's law, the first Kirchhoff's law is that the current at a junction is the same. So what we do is we imagine that we have a battery here. We imagine that we have a battery, and let's say the voltage on the battery is, well, it doesn't really matter what it is. I'm just going to say it's V. And at this junction, so the current flows from the battery here, like this, like this, like this, and then it goes like this, 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 like this. The problem is we don't know which way it will flow here, so we guess. Okay, so we label the currents. We label this as current I1. We label this as current I2. And let's say the current flows here, which actually makes sense, I3. This is still I3. Now, if you look carefully at this system, you will see that this is also I2. Ikshita, I'm not sure I understand the question. This is a problem similar to, I just want you to, I want to show you this. This one, problem 10. It had 3 stars, so it's a really tough question. So what you do, you label the currents. You don't know the currents. You don't really know the voltage. So, and then the current goes like this. If you look at, the system is symmetrical. And because it is symmetrical, you will notice that I1 has to equal to this I1, and I2 has to equal to this I2. Is it I2 because it has the same resistance? Well, yes. The pathway, look, we're looking at 2 different pathways of current. So the current flows here, let's call it I0, and it splits into 2. So the current has a choice whether to go left or right. And if you look closely, the path on the left is no different from the path on the right. I don't have a lot of time to go through this in detail, but this is how it is. And then you use the Kirchhoff's second law. Kirchhoff's second law says that in any loop, the total voltage is the sum of potential drops and rises is 0. You know what? I have done a webinar on this, and I've actually gone through this, a very similar question to this. And unfortunately, I don't have time to finish this today, but I will tell you where to look for it. So if you go to YouTube, You go to the playlists and COMPOS Year 12 webinars. COMPOS Year 12 webinars. And DC electricity part. So webinar 27 and 28. So this is where you can find webinar 27 and 28. That's you can find very similar problems to that. So this is for you have to realize that this is just for the hardest question on the paper. It's 3 stars. Anyway, I really want to spend some time going through this model. So one of our students has kindly drawn some very nice pictures for us. And right. So what do we see here? We see water. We see a water pump. A water pump raises water to a higher level. The same way the battery as the battery moves the charge from here to here, it raises the potential. Raises potential energy. Energy of charge. And this raises the potential energy of water. Then the water flows through a very wide duct with no resistance. So no resistance here. Resistance. So there's no energy lost in this wire. So there's no energy lost along this wire. And then at C, it goes through a very narrow duct. As it goes through the narrow duct, it loses potential. So it loses energy. So energy lost. Just like electrons lose energy as they go through a resistor. And then they go through a second duct, so the second resistor. So a narrow duct is like a resistor. And they fall through this narrow duct and they lose energy as well. This energy is dissipated as heat. Just like in a resistor, energy is dissipated as heat. And then the water goes back to the pump to get more energy. So the electrons, they go back to the battery to get more energy. So they're raised again to a higher potential. They get given potential energy, and then they spend that energy through the resistors. The same thing goes here. Now here, this is a parallel circuit. The water can spend its energy in this duct, which is wider, or through this duct, which is narrower. And understandably, we have more water flowing through this one because it is wider. So it's a lower resistance. So let's take a picture. So this is low resistance. This is high resistance. But you see the voltage drop, the drop in energy is the same for both ducts. So that's why the voltage in parallel is always the same. Voltage in parallel is always the same. Yeah, V1 and V2. They say that voltage in parallel is the same. This is, you can see from the example of water that the voltage V1 and voltage V2 is the same. For V1 is the difference in height. Right. So I really have to go. Next week we are going. I'll do a mix. I'll do a mix of maths and physics. Probably more physics because I think it might be. Yeah. But please come with your questions, and I will be happy to to answer. So see everyone next week, and well done. I apologize if when do we need to hand in the enrollment form by? Well, next by the end of this week is fine. But yes, we won't be able to do anything until the end of the week anyway. But yeah, as soon as possible, please. When we are older, if we're able to go to Oxford, can we become a tutor for COMPOS? Aha, that's an excellent question. Look, the students who finished year 13 last year, they are now at university in year 1, and when they next year they go to year 2, and when they in year 2, we invite them to become tutors. So yes, we would like you to eventually become COMPOS tutors. And this can happen, the earliest that it can happen is when you go into year 2 of university. And you don't have to go to Oxford, no, because you know that if you've done the COMPOS program, we'll be happy, whichever university you choose to go to, I'll be happy to take you. Yes. Even if even if for some reason you decide not to do physics, which would be weird. All right, excellent. See you. Happy Halloween. Yes. I got my costume.